Hello all. So today we will be discussing about the TIFR 2020 paper, question number 3. So I will share the screen with you. The question will be there in front of your screen. If you want to solve the question by yourself, then you can pause the video and start solving on your own. And and uh, after you have done it, then you can actually check the solution. So let's get into the solution of the question. Let's first see the question. So the question is like this, that if f is a function from R to R, it's defined like this, then which of the following statement is correct, right? So here are some facts that we will be using, and first I will, as a hint, write down the facts, and then I will write down the solution step by step. So see, there are two things that we need to consider here. So in this problem, as you can see, that there are many options. Right? It is a surjective function. It is bounded. The derivative of it exists and is continuous on R, so on and so forth. Like the zero set of this function is finite. Now, the first of all, zero set of this function is never finite, because we know that this is a very famous function. So geometrically, you can see that there is a huge oscillation of the graph in a small neighborhood of zero. There are huge oscillations. Like in a very small interval, there are many oscillations. So because of this, the finite set criterion actually goes out of the window. Now the derivative of f exists and is continuous on R. So as you can see that since it is sine 1 by x, so the derivative will have cos of 1 by x, right? And if it is continuous, so if you just take the derivative of this function, then it will look something like this: x sine 1 by x plus x square cos 1 by x into minus 1 by x square, right? So this goes up. Then we can directly write that the derivative kind of looks like this: minus of cos 1 by x. But there will always be a problem when limit x tends to 0 of cos 1 by x. Okay? So the derivative of f exists and is continuous on R. So for it to be continuous, it needed to be at least defined at x tends to 0. And like f of 0, f prime of 0 has to be limit x tends to 0 f prime of x, but both of these things are not possible. Secondly, f is bounded. So these two options you can kind of verbally eliminate, option D and option C. And for option D, as you can see, you can use the squeeze theorem, right? And you can also see this without using of the squeeze theorem, like this, that if you take x square sine 1 by x, so if you take x square sine 1 by x, then you can actually write it like this: x sine 1 by x by 1 by x, right? So if you take x tends to infinity, then this will shoot to infinity. So if you take limit x tends to infinity, okay? Because this is practically 1 and it will solely depend on where x is heading. It will be solely dominated by x. So hence the bounded option is also not there. So since it's an MCQ, by option elimination, you can say that f is a surjective function. But how to mathematically understand that f is itself a surjective function? So the first of all is, if you look at the function f of x equals to So let me write it down. So we are trying to prove that the function is surjective. Right? So this is to show. So if I have fx equals to x square sine 1 by x, then x square, as I just mentioned, this can very well be written like this: x into sine 1 by x by 1 by x. All right. So the moment you write it like this, then you can say that if x tends to 0, then this will go to 0, because again by so limit x tends to 0, this will go to 0. You can directly write it like this, or you can use the squeeze theorem, that this is in between x square and minus x square, because sine 1 by x, no matter whatever the value, is always between 1 and minus 1. So by usage of the squeeze theorem or sandwich theorem, you can write down that f of x tends to 0. So this is the, I mean, this is pretty straightforward, but limit x tends to 0, f of x is equals to 0, which is also happens to be f of 0. Now the way our function is defined, as you can see, that apart from the only problem point is x equals to 0. So apart from that, everybody is continuous, right? So sine 1 by x, the only problem is in this x, when x is becoming 0. But apart from that, it's continuous. At 0, we have proven it's continuous, and it's a continuous function. Now, moreover, what happens is that, so let us go to the function. So I have limit x tends to 0, f of x is 0. Limit x tends to infinity. If you look at limit x tends to infinity, then this is what? Then this is again x sine 1 by x by 1 by x, and hence it is infinity. So it will shoot to infinity because it's always getting dominated by x. And since if you take limit x tends to minus infinity, then what will happen is x sine 1 by x by 1 by x. This will shoot towards minus infinity. Now you have a continuous function. You have a root at a point. F of 0 is 0. If x tends to infinity, it is going towards positive infinity. If it is minus infinity, then it is going towards negative infinity. So that means what? The immediate theorem that comes to your mind is what? It is the intermediate value theorem. Okay, so intermediate value theorem. Okay, so practically IVT. So what does IVT tells us? IVT tells us is that if it is x tends to infinity, it is shooting towards infinity, minus infinity, it is shooting towards minus infinity, then there will always be a point where I will always have a root. Now, if I want to write it down properly, it's like this, that since the function that has been given, it is defined from R, R, and we need to prove that it is surjective. What am I actually trying to prove? That given a y in R, there exists a x in R such that f of x equals to y. This is exactly the thing that I'm trying to prove, right? So now what happens is, if you pick an y, you need to figure out that what is that, or let's say x naught. At least there is an x naught such that f of x naught equals to y. So you need to figure out what is this x naught here is. So what we do is we take the function g of x equals to f of x minus y. Now what happens is, at x tends to infinity, g of x will tend to infinity, because we have proved that fx is shooting towards infinity. At x tends to minus infinity, g of x will tend to minus infinity. similar reason that fx tends to minus infinity, which implies that whenever this is practically happening by the intermediate value theorem, there has to be a point where you will have, so then there exists an x naught such that g of x naught is actually equals to 0. So the moment g of x naught becomes 0, what happens is you get f of x naught equals. So this is precisely what we wanted to figure out, that for a given y in R, does there exist an x naught in R such that this x naught maps to y? That is how the surjectivity proof is done. So what we have learned from this question is how we eliminated all the other possibilities and we came up with the correct answer. Okay. So in exam, even if you are unable to solve directly, you can always count to the method of elimination. So here, as you can see, that we firstly eliminated all the other three options, and since it is MCQ and none of, and that is why you have to also read the instructions very carefully, because in TIFR 2020, none of the above was not an option. Like if none of the options given are true, you can write none of the above. This is not something that was given as an instruction in TIFR 2020. So one of these options has to be the answer, correct? If three of these are eliminated, then the obvious choice is the first one, and we explicitly deduced how to get to the first one. So what are the steps? The steps are first to understand that intermediate, how to, I mean, it's the only thing that we use, how to use the intermediate value theorem properly. Okay, then see you guys. So next time we will be meeting with TIFR question number 4. Thank you for joining us. Okay, so the derivative, it's not continuous. It's because this. So if you take f of x equals to x square sine 1 by x, all right? So then what is f prime of x? This is 2x sine 1 by x minus cos 1 by x, right? Now, what is the problem point? The problem point is 0. So everywhere else, this is differentiable, hence it is differentiable. The only problem is that is it differentiable? I mean, so is it differentiable at 0? And if it is differentiable, then is it continuous? So to prove that it is continuous, what do I have to show? I need to show that limit x tends to 0, f prime of x is equals to f prime of 0, right? This is precisely what I have to show. But f prime of 0 itself, if you go through the problem, then it is 0. But limit x tends to 0, there won't be anything to bound cos of 1. I mean, there is no limit there. So the continuity gets violated because you won't be having this property of the differentiability. Okay. So for that, I mean, limit x tends to 0, f prime of x is not equals to 0. F prime of x is not equals to f prime of 0. That's the reason. All right. Okay, then see you. We will meet next time. Thank you for joining.